Hi there, Miss Barbara here. This lesson is titled The Law of Sines. The objectives of this lesson are 1. Be able to apply the law of sines. 2. Be able to apply the law of sines to the ambiguous case. And 3. Be able to solve applications that require the law of sines. Roman numeral 1, the law of sines. In general, a triangle is determined by 3 of its 6 parts. It's 3 angles and 3 sides as long as at least one of these parts is a side. The possibilities are, with case 1, 1 side and 2 angles. These are known as angle side angle or side angle angle. Case 2 would be 2 sides and an angle opposite one of those sides. This is known as SSA. Case 3, 2 sides and an included angle. This is often abbreviated as SAS. And case 4, 3 sides, abbreviated as SSS. Cases 1 and 2 can be solved using the law of sines. The law of sines states that in any triangle, the lengths of the sides are proportional to the sides of the corresponding opposite angles. For the triangle ABC, the law of sines states that sine A is to A as sine B is to B as sine C is to C. A pilot is flying over a straight highway. He determines the angles of depression to 2 mileposts, which we'll denote as A and B, that are 5 miles apart, to be 32 degrees and 48 degrees. Find the distance of the plane from point A. Well, let's first get a sketch. There's 2 mileposts, A and B, and the distance between those 2 mileposts is 5 miles. We'll say the airplane is flying above that somewhere, and so there's a triangle. Now, let's go ahead and get angles of depression. Okay, the angles of depression from the mileposts, we'll call one of them 32 degrees, and the other one is 48 degrees. The question that is being asked is, what is the distance for little b? That's the length opposite angle B. So we're going to have to use a little bit of geometry to get some measurements of angles that we need. Let's first find measurement for angle, let's call this distance C, so angle C. Okay. We have a straight line across the top, and so a straight line is 180 degrees. We've got 32 degrees and 48 degrees, the sum of which is 80, so the remaining angle here will be 100 degrees. Now recall way back from geometry, if you have 2 parallel lines, then the measurements of the alternate interior angles are the same. So, for the 32 degrees, that corresponds to the measurement for angle A, and for angle B, that is the alternate interior angle to the 48 degrees given. So now we have all 3 interior measurements, and we need just B. So using the law of sines, we'll do B. Sine of B is equal to, let's do C, sine of C. We need to solve for B, so B would be equal to C times the sine of B divided by the sine of C. And let's put the numbers in. The length for C is 5 miles, and we want the sine of B, which we know is 48 degrees, and we're going to divide that by the sine of C, which we computed as 100 degrees. Let's use a calculator to get an approximate value for this distance. You are looking at a TI-84CE screen. Let's compute. We're going to do 5. Find the sine button, sine of 48 degrees, get an output, and let's divide that by the sine of 100 degrees, And the output looks like 3.773045161. Let's transfer the answer to our workspace, and that would be 3.77 miles. Solve the triangle ABC given angle A equals 23 degrees, angle B equals 110 degrees, and the length of side C equals 50. Let's draw this triangle. My drawing will not be to scale, but it's for the purposes of labeling. So on one angle, A, that's 23 degrees. The other angle, B, is 110 degrees. We are not given the measurement to angle C, but the side opposite that, the length we're given is 50. Notice that we are given an angle, side, angle set of measurements. Now let's use the law of sines to see where we can get. But before we do, let's go ahead and get the measurement for angle C. Remember, if we want angle C, okay, that's going to be the total number of degrees possible, which is 180 degrees, minus the sum of the other two angles we have, which would be 110 degrees plus 23 degrees. So performing that arithmetic, we'll get that angle C is 74 degrees. Now we've got two sides remaining to get. Let's get B first. So using the law of sines, sine B is to sine B as C is to sine C. I like to algebraically isolate what we're solving for first. So we'll say that little b is equal to the length C times the sine of B divided by the sine of C. Let's put our numbers in. Length of little c is 50. Sine of B was given as 110 degrees, and we want to divide that by the measurement we just got for sine of C, for the C, so it'll be sine of 74 degrees. Now let's use technology to get an approximate measurement for the length of B. I am looking at a TI-84 screen, and we need to compute the values to get us the length of B. So we'll have 50 times the sine of 110 degrees. Let's go ahead and get the output for that. And we want to divide that number by the sine of 47 degrees. And the output is 64.2433767. Let's go to two decimal places and use that as our measurement as we continue. So we will use 64.24. Now, let's see, what do we have? We have angle C, which we got as 47 degrees. We got the measurement for length B, which we just computed as 64 point, and let's just round it down to 2. And what we have left to solve is the measurement of the side length A. So let's use the law of sines again. So that's our third part that we're solving for. We'll have A is to sine of A as, let's do C is to sine of C. Let's isolate the A. So A is equal to C times the sine of A divided by the sine of C. And let's put our numbers in. So we'll get that the length A is equal to 50 times the sine of, what is A? Oh, 23 degrees, that was given, divided by the sine of C, which we just computed, is 47 degrees. Now, let's use technology again to get an approximate value for the length A. Again, I am back at a TI-84 screen. Let's compute 50 times the sine of 23 degrees. I'll get an output for that. And let's divide that, come on, divide, by the sine of 47 degrees. And the output is 26.71287,009. Let's transfer that to our workspace. And we got 26.71. So for where we're listing it, let's write that as 26.7. And here we solved that triangle. Roman numeral 2, the ambiguous case. Thus far, our solutions have resulted in a unique triangle. This is not always the case. When presented with measurements for two sides and one angle, we may have two triangles, exactly one triangle, or no triangle with the given properties at all, which brings us to the ambiguous case. The triangle situation given in case 2, in which two sides and an angle opposite one of those sides are known, is sometimes called the ambiguous case because there may be two triangles, one triangle, or no triangle with the given properties. In general, if sine A is less than 1, we must check the angle and its supplement as possibilities because any angle smaller than 180 degrees can be in the triangle. To decide whether either possibility works, check to see whether the resulting sum of the angles exceeds 180 degrees. It can happen that both possibilities are compatible with the given information. In that case, two different triangles are solutions to the problem. Solve the triangle ABC given angle A is 135 degrees, the side opposite that, length little a, is 100, and another side measurement is C equals 80. We have an ambiguous case because we are given measurements of two sides and one angle, which means we could have two different triangles, one unique triangle, or no triangle at all that satisfies this criteria. Let's begin by sketching in a triangle with these values. My triangle drawing will not be accurate to measurement. I'll make one angle, 135, that's A. The side opposite that is 100. Then we have a measurement for side C. We'll just call one of the sides C. That's 80. And so the angle opposite that side will be capital C, and then we have B's remaining for the remaining corner and remaining side. So let's begin this by using the law of sines, and I'll begin by looking for the angle measurement for C. So I'll do sine of C is to C as sine of A is to A. Let's algebraically solve for sine of C. So sine of C is little c times sine of A divided by A. Let's continue with this but put in the numbers. So now we'll have sine of C is equal to, and for little c we'll put in the numerical value of 80, and then the sine of the measurement is 135 degrees divided by length A, which is 100. Okay. Use your calculator to get an output for the expression on the right-hand side, and you'll get that sine of C is equal to, and the value that I got is 5.56568544249. It's real important that you don't truncate during computation. Now we need to actually get the measurement for C, so we'll say C is equal to the sine inverse of 0.56568544249. Now use your calculator again and compute that, and we'll get that the measurement for angle C is 34.44998 degrees, and so we'll round this angle C to 34.4 degrees. Now let's solve for the measurement of angle B, which will be pretty straightforward because that's going to be 180 degrees. Remember, the sum of all the interior angles of a triangle is 180 degrees, so we'll do 180 minus the 135, which was given, minus the 34.4 that we just computed, and Doing that arithmetic, we get 10.6 degrees for angle B. The only thing left remaining to solve is going to be length B, so let me get some more space for that. Continuing with the law of sines, we know that B is to sine B as A is to sine A. I want B, so let's solve for B. So we get A times sine of B divided by sine of A. Let's replace those with numbers. So the value that we have for A is 100. We want the sine of B is the measurement we just solved for, so that's 10.6 degrees, divided by the sine of A, which was given, is 135 degrees. Use your calculator to get an output. Make sure that you confirm the output. I got 26.014649999, and let's just round it to length B is 26. So the measurements that we solved for, we got angle C was 34.4 degrees, and angle B that we just used was 10.6 degrees. Because the measurement that we were given was 135 degrees, we know that it's only going to give us one unique triangle. Solve the triangle ABC given angle A equals 30 degrees and two sides, A equals 75 and B equals 100. Remember, when given two sides and an angle, we are looking at the possibility of an ambiguous case. We could have two triangles, no triangles, or one unique triangle. Let's remember that as we set up the triangle. Obviously, my drawing will not be accurate. It's for the purposes of labeling. I'll pick one angle as B, and the side opposite that, the measurement, is 100. We are given a measurement for angle A, which is 30 degrees, and the side opposite that, the measurement, is 75. And so let's just pick C for the remaining vertex, and side opposite that will be the length C. When we finish, we need to end up with a measurement for angle C, a measurement for angle B, and a length for the one missing side. Let's begin by looking for measurement angle B. I will start with sine of B is to B as, let's do sine of A is to A. Continuing, I'll solve for sine of B. So sine of B is equal to B times the sine of A divided by A. Let's replace those with the values we have. So sine of B is equal to, the length of B is 100, and we want the sine of 30 degrees, which is really nice, and we'll divide by the length A, which is 75. Okay, sine of 30 degrees is a half, so we have 100 over 75, which is 4/3 times 1/2, which gives us an output of 2/3. Let's continue. We need B. So if sine of B equals 2/3, then B is equal to the sine inverse of 2/3. We'll have to use technology to get an approximate value for that. Again, using a TI-84 screen, let's go to sine inverse. That's second function, sine. That gives me the sine inverse symbol. And we'll do 2 divided by 3, close parenthesis, enter. And I get 41.8103149. Let's just go to one decimal place and we'll use the 41.8 as the degrees. So we have that B is equal to 41.8 degrees. Now, that can be used as a supplementary angle. So we have to know that if you do 180 degrees minus 41.8 degrees, okay, that measurement is 138.8 41.2 degrees. And guess what? The sine of 41.8 degrees and the sine of 138.2 degrees is exactly the same. We have a situation in which we will have two triangles. So for this, we're going to solve for two different triangles. We'll do one, we'll call it B1, and that was the 41.8 degrees we would get in the first quadrant, and the B2, for which you get the exact same sine output, is 138.2 degrees. Now we just need to solve for the remaining C1 and the length C. Let's solve for C1. A triangle has 180 degrees, and so C1 is going to be 180 degrees minus 30 degrees minus 41.8 degrees, and that will give us 108.2 degrees. So now we've got all three angles, and we need to solve for the length, little c1. Let's use the law of sines for it. So we'll write c1, sine of c1 is equal to a sine of a. Let's just solve for that c1 by itself. So we'll have a times the sine of c1 divided by the sine of a. Let's put the numbers in now. Okay, so the length for a is 75, and we've got the sine of c1 was the angle measurement we just got, so that's 108.2 degrees, and we want to divide that by sine of 30 degrees. I will trust you to use your calculator to get the output. I got 142.495. We'll round that to 142.5. So for the measurement of B1 equals 41.8 degrees, the length C1 is 142.5. Now let's go ahead and get the values when we let the angle for B2 be 138.2 degrees. So the corresponding angle C2 is going to be 180 degrees minus 30 degrees minus 138.2 degrees, and that difference will give us 11.8 degrees. And now we need to get the measurement for the length C2 that corresponds to these angle measurements. So we know that C2 sine of C2 will be equal to a sine of a. So let's solve for C2, and we'll get C2 is equal to a, the measurement of 75, times the sine of 11.8 degrees for the sine of the C2 measurement, and we'll divide that by the sine of 30 degrees. Put that in your calculator, and the output that you get, make sure you verify, is 30.67 in length. So notice that this one, in the ambiguous case, we got two different triangles that have an angle of 30 degrees and a side opposite the 30 degrees of length 75 and another side of 100. Solve the triangle ABC given angle A is 50 degrees. The side opposite that, length A, is 50 and length B is 100. Let's begin by drawing the triangle that fits these requirements. So we have three sides. I'll pick one angle, call that A, and that's 50 degrees. The side opposite that is length 50. We'll label the remaining angles B and C. The side opposite the angle I labeled B is 100. Obviously, my drawing is not to scale. That's okay. And we're still looking for C. So let's begin by using the law of sines. We have two sides and one angle, so we have enough information for that. I'm going to begin by looking for the measurement of angle B. So using the law of sines, I'll have sine of B is to B as let's do sine of A is to A. It's good practice to algebraically isolate what you're solving for first. So let's go sine of B is equal to, then multiplying the B through, B times the sine of A divided by A. Now we can put our numbers in, and we'll get sine of B is equal to, the length we have for B is 100, times the sine of the measurement for angle A is 50 degrees, divided by the length given as 50. Okay. Let's use a calculator to get that value. This is a TI-84 screen, and I am looking for the product of 100 times the sine of 50 degrees. Let's go ahead and get that value and then divide that by 50. The output is 1.532088886. So transferring, it was 1.532088886. And we need to get B by itself, so what we really need is B to be equal to the inverse sine of 1.532088886. You don't need a calculator to know that this is not defined. The range of the sine function has to be between -1 and +1, and this value is greater than 1. So even without a calculator, we know that this is not defined. Okay? You can check if you want to, so let's do that. We are back in the calculator screen, and let's do sine inverse. So second sine makes the sine inverse pop up. I'll use the arrow to capture the output, press enter, and look what happens. It says error domain, and we knew that. And so at this point we conclude, therefore, no triangle exists for this criteria.